in this section, we're going to start with the planar kinetic equations. That's basically Newton's second law for rigid bodies. Remember, these rigid bodies are rigid bodies in 2D, in 2 dimensions, so that so there is a symmetry there to consider. And so, and the most general motion we have to remember is composed of a translation and a rotation, and we want to write equations of motions that have that feature. So this is a picture that we have to keep in mind. So we are going to have a rigid body, and that rigid body has a center of mass G, and then there is a point P in the body where we are going to attach a coordinate system, and the body might be rotating about that point, and that point might be moving or not. And so that's a generic point. So there are forces acting on the body as well as moments, M1 and M2. And then there's an acceleration of the whole body, and then there is an angular acceleration, and then there is an angular velocity. So keep this picture in mind, and in particular the difference between this point and this point here. So now, if the body is just translating, then all we need to do is write Newton's second law for the center of mass, as we've done before, and we are done. And that's it. That's all we need to do if there's only translation. So now, in the case we have rotation and translation, things are more complicated. And we are going to start by looking at how this works. So imagine a point P, a generic point I here on the body, right? So that point has a position R, right? And there are forces acting on that body. This capital F, that is going to be external forces, and lowercase f, that is internal forces, forces due to other particles on I. So the net force is just external plus the internal forces. So we can write Newton's second law as external forces plus internal forces is equal to mass times acceleration for that particle I. So now I'm going to multiply by the position vector, right? So that comes as R cross Fi plus Fi, right? That's equal to R cross, and these are vectors here, right? So I haven't done anything, just multiply by R or take the cross product. So this is the moment about P of particle I. That's what this is. And then this is R cross Mi. And now this acceleration, remember how we write this acceleration? We can write this as the acceleration of point P plus the rotational part, and the rotational part is alpha cross R minus omega squared R. So this is from the previous chapter, right? So that's all. So now let's just do a simplification here. So I get the moments about P for particle I, that is equal to Mi, and then I get R cross AP plus R cross alpha cross R minus omega squared R cross R. Now we know from properties of the cross product that this is 0, so all we are left here is that the moments about P of particle I are equal to the mass times R cross the acceleration of point P plus R cross alpha cross R. So that's all there is for particle I. So now what I want to do now is I want to add over all the particles, right, on the body, right? So I'm going to do a sum in I, and so I'm going to do a sum here, and I'm going to break this as the sum in I mi r cross rp. And now I'm going to remember that this is the position of particle I, and I'm adding all those particles there, right? And then I'm gonna have here to summon I, mi ri cross alpha cross I. Remember, alpha is the same for all particles because the body is rotating as a whole. So now, what is this? Well, these are the moments about P on the whole body, right? So I'm going to write this as MP, right? This here, you can see that the acceleration of point P actually doesn't depend on the sum, and this sum here is just the mass of the body, and I'm going to call that M, right? The mass of the body times the position of the center of mass. So this is G here. This is G cross AP, right? So that's that equation there. And this one here, what this is going to become, this becomes the moment of inertia about P cross alpha. You see, you have an mi and then the r squared here, mr squared, that's the moment of inertia. Alpha actually doesn't depend on the sum. And so when you simplify this, you can do this. And it is done in pages 424 and 425. When you do this, then that's the final equation that you get. So this is the final equation. So that's the moment of inertia about P are equal to the mass times the position of the center of mass cross the acceleration of AP plus IP times alpha. Now, if this point P, we choose it to be alpha, what we get is the moment about G, right? And this should be a sum here because there might be more than one moment. These are not the same sums though. And so that is equal to Ig times alpha. So that is one equation that we need to keep by. So now we need to do a little more simplification on this equation. So, and we'll do that in the next video.